next context is equilibrium of rigid body. When we call equilibrium, this means acceleration of the rigid body is 0. When acceleration is 0, we have two equations for translation. When translational acceleration is 0 or linear acceleration is 0, F is equal to m into a. When a is equal to 0, the net force acting on the rigid body will be equal to 0. So this condition, either F net force or F is equal to 0 or the acceleration of the body is 0, both are same thing. This is called translational equilibrium. When the angular acceleration of the rigid body is 0, you can call it rotational equilibrium. For rotational equilibrium, when you put alpha is equal to 0, the net torque acting on the rigid body about any point of reference will be equal to 0. So tau equal to 0 or alpha is equal to 0. Both the conditions are the conditions for rotational equilibrium. But we have a case of statics. Statics means the body is at rest. Suppose you put the body here. This is in equilibrium because it is not accelerating, but this is a case of static. This is stationary, a case of static. Statics means velocity of the body is 0, angular velocity or linear velocity. So we will be discussing the equilibrium of rigid bodies. For instance, this rigid body is folded in this direction by an external force, and gravity is pulling it down, which is acting at the center of mass. The gravity is producing clockwise torque, and this force produces counterclockwise torque. This torque produced by the external force, torque produced by gravity about this point P. So this is a clear-cut case of equilibrium because alpha is equal to 0. When alpha is 0, the net torque is 0. About which point? Your choice. Either you can take any point, it may be pivot, it may be any other point, or it may be center of mass point. Net torque is 0. Because torque tau p is equal to ip into alpha for fixed axis. Tau c is equal to ic into alpha for center of mass axis. The condition for equilibrium is alpha 0. Which equilibrium? Rotational equilibrium. When alpha becomes 0, tau c will be 0 and tau p also will be equal to 0. So when alpha becomes 0, tau p and tau c both will be equal to 0. P you can take any other point outside the body also, doesn't matter. It may be pivot, it may be center of mass, it may be any point outside the body, but should be fixed or should be moving with constant velocity. So the points must be, the reference points must be inertial. But another interesting thing I would like to tell you. When the body is in equilibrium or rotational equilibrium, already you have proved that torque about center of mass is 0 and torque about any point will be 0, and this point must be inertial, a reference point. This is the center of mass point. Now question arises. Here P we are taking inertial point, and the velocity of this point is constant or it will be equal to 0. 0 also is a constant quantity. But for center of mass point, there is no such restriction. The center of mass may be moving with non-uniform velocity. For instance, center of mass acceleration is AC. When you stand on the center of mass, you have to impose a pseudo force because you are standing at the center of mass which is accelerating. So this is a non-inertial frame. Let the center of mass move with an acceleration. AC say. Therefore, this is a non-inertial reference frame. For non-inertial reference frame, we have to impose a pseudo force. We have to stand on the non-inertial reference frame and impose a pseudo force. The pseudo force always acts, in this case, for translation case, is always acting at the center of mass, MAC, in opposite direction of AC. This pseudo force along with the external force, say gravity acts at the center of mass and external force acts at the center of mass. Imposing a pseudo force at the center of mass, then you have to write the torque equation, tau C is equal to IC into alpha. Alpha will be equal to 0. So tau C is equal to external torque, or torque produced by the external force, plus torque produced by gravity, plus torque produced by the pseudo force is equal to 0. And if you take the pivot point, we have the torque equation says that tau P is 0. For tau P is 0, we have two forces, gravity force, external force, and of course we can impose, or you can write reaction forces, components along x and y direction. Or you don't like this, you can write some net reaction force R. The reaction force passes through this pivot, therefore it cannot produce a torque. The torque is produced by gravity, torque is produced by the reaction force even though it is 0, plus torque is produced by the external force will be equal to 0. So these two torques will be equal and opposite. Come to this. In this case, the pseudo force passes through the center of mass. Even though the center of mass is accelerating, the pseudo force passes through the center of mass, it cannot produce a torque about the center of mass. Therefore, always the torque of these two forces will be equal to 0. So, torque of the external force and gravitational force can be equated about this point, or it can be equated about center of mass point. There is a clue. There is a point here about center of mass, or about this point, or about any other point inside, suppose Q, or outside M, this outside point, and these are the inside points. This is a 5 hot, the center of mass, any inside point, any outside point. Can you equate the torque of this two or of all this to 0 about any point? In this case, yes, of course we can equate, because alpha will be 0, therefore net torque will be 0 about any point we have shown. About this point net torque 0, about this point net torque 0, about this point net torque 0, about this point net torque 0. Let us refine the discussion on the equilibrium of rigid bodies by taking, let's take an example. Then I will be coming back to the theory and refine the theory by doing some problems. You take a rod pivoted here at the end point, and you hang the rod by a string so that the rod will not move. The velocity of the center of mass is 0 and the angular velocity of the rod is 0. How we can see? The rod is not at all moving. Angular motion 0. No angular motion and no linear motion. Linear motion is characterized by the center of mass velocity. Angular motion is characterized by the angular velocity of the rod, both 0. If linear velocity of the center of mass is 0, we can say linear acceleration of the center of mass also will be equal to 0. When the angular velocity of the rod is 0, we can say angular acceleration, that is d omega by dt, will be equal to 0. AC is equal to dv by dt will be equal to 0, or dvc by dt is 0. So, this is the condition for rotational equilibrium. This is the condition for translational equilibrium. Therefore, the rod is possessing both the types of equilibrium, rotational and translational. Under the action of the string force, that is tension, the gravity force, and the reaction force given by the rod. Along this direction there is no reaction force, very easy to understand. So, if we draw the FBD, we are having 3 forces. One, the reaction force, or you can write, since the reaction force is normal, this is called normal reaction force. This is gravity acts at the center of mass of the rod. Tension is here at the end of the rod. So, these are the given conditions. By seeing the physical picture, physical situation, you can understand Then you can write Newton's laws of translation and rotation, or force equation and torque equation. Write force equation. F is equal to ma. Along this it's not accelerating. Or if you impose any reaction force, suppose Nx, this is Ny, you write Fx is equal to m into x, is the acceleration of the center of mass. Fy is equal to m into ay. Then you can write torque equation. Tau z about center of mass. We write the torque IC into alpha, or about this point P also you can write the equation IP into alpha, or about this point you can write IQ into alpha, or you can choose any other point outside also, doesn't matter, or any other point you can choose inside also, doesn't matter, or let us come to the force equation. Here we have x0, ay0, alpha 0. Since x is 0, net force along the x direction acting on the rod, we have assumed Nx. So there is no reaction force acting on the rod in horizontal direction. Fy is two forces along positive y direction, up, one force down, up force is positive, down is negative. So T plus Ny up, down force minus j cap. These two forces, up forces, are having plus j cap direction, therefore positive. Ay, what is Ay? 0. So T plus Nay is equal to mg. Equation number 1. Equation number 2. Next, you can write torque equation. About the center of mass also you can write. About the center of mass, this force passes through the center of mass, cannot produce a torque. A torque is produced by these two forces. This produces clockwise torque, this produces anti-clockwise torque. So torque due to Ny plus torque due to Nx plus torque due to T will be equal to 0, because alpha is 0, because it is possessing rotational equilibrium. Well, since Nx passes through the center of mass, it cannot produce a torque about the center of mass. Ny is producing a torque that is equal to Ny into L by 2. If the body is uniform, needless to mention, it is a uniform object, and therefore center of mass is located at the geometrical center, at the midpoint of the rod. Well, which direction? Minus k cap. Due to the tension, it is positive, means along plus k cap, or anticlockwise L by 2. In this way, you can conclude that both normal reaction and tension, both the forces are equal. If you take the reference point, the pivot, about the reference point P, also you can write force torque equation. These two forces pass through this point, cannot produce a torque about. The torque is produced by gravity and the tension. So if you take the gravitational torque is anticlockwise, and torque produced by the tension is gravitational torque is clockwise or in, and this tension about this point produces a counterclockwise torque, whereas the tension tends to rotate the rod in this way, and gravity tends to rotate the rod in opposite way, in clockwise way. Tension tries to or tends to rotate the rod in positive z direction or anticlockwise manner. So gravitational torque tau n plus tau g plus tau t is equal to alpha is 0. This force reaction Nx and Ny pass through this point cannot produce a torque, so this will be 0. Gravity produces a torque, that is negative mgl by 2. Tension produces a torque, this distance from the tension line of action of this force at this point is L, mgl, and the angle is 90 degrees, sine 90 is 1. In which direction? Positive direction. I am not writing kf again and again. If it is positive plus, if it is negative minus. Simply you can write like that. So this is not mg, this is the tension. So in this way you are getting T is equal to mg upon 2. Or if you choose this equation, or if you choose this equation, any one you can choose, or if you choose the reference point Q, also you can take the torque of this force, this force, this force, and this force. This force passes through this point Q, cannot produce a torque, and the Nx passes through the point Q, cannot produce a torque. Therefore, torque is produced by Ny and Mg. Ny produces clockwise torque, Mg produces anti-clockwise torque, because this tends to rotate the rod in this way about this point, and gravity tends to rotate the rod in this way about this point. That's the idea. So tau q is equal to IQ into alpha. Alpha is 0 for rotational equilibrium. Therefore, tau q is 0. Tau q, torque about q, is produced by Ny, Nx, gravity, and tension. This is vectorial. Nx passes through this point, cannot produce a torque. This is very thin. Tension passes through this point, cannot produce a torque. So torque is produced by both. So Ny produces a torque. How much? This is a line of action, this is the point. What is the perpendicular distance? L. And direction? Minus k cap. And gravity produces a torque which is equal to mgl by 2 in k cap direction, that's equal to 0. So here you are getting Ny is equal to mg. Either this equation or this equation or this equation. Either you choose reference point C or reference point P or reference point Q. Either you can choose reference point C or P or Q, your choice, or any point outside also. But this three, if you choose, you can get some mathematical advantage, because some forces may pass through. If you choose P, these two forces pass through this point, cannot produce a torque. If you choose C, this force passes through this point, it cannot produce a torque. If you choose this force and this force, these two pass through this point, cannot produce a torque. Some mathematical advantage you are getting. Well, so we can get some answers. In terms of the weight of the body, let us calculate tension, reaction force along x direction, horizontal reaction force and vertical reaction force. Nx is equal to 0. Next, if you choose the point P, T is equal to mg by 2. If you choose Q, Ny is equal to mg. Mg by 2, it's not mg. We have sometimes we have slip of hand. It's not mg, mg by 2. So what is the use of this equation then? If you put ny is equal to t, if you use this reference point and this torque equation and this force equation, you can solve this to get equation 3 for this reference point and equation 2. If you solve, you are getting 2t is equal to mg or t is equal to mg by 2. And when ny is equal to t, ny also can be equated with mg by 2 and x is 0. So in this way, you can write force equation with respect to the ground frame or torque equation with respect to any point, this point or this point or this point or any other point outside the rod, doesn't matter, you are getting the same answer. This is the simplest problem of the rigid body, the rod possessing both translational and rotational equilibrium. The context is equilibrium of rigid body. For translational equilibrium, center of mass acceleration must be 0. For rotational equilibrium, the angular acceleration of the rod will be 0. So for this, net force acting on the body will be 0. Net torque acting on the body will be 0 above any point. Let us take next example. The same rod, which is pivoted at the point P, is in equilibrium when the end of the rod is connected with this roof by an inextensible thread which is not vertical. Now here the rod is inclined at an angle theta with respect to the rod. In this case, we need to calculate a reaction force, vertical, a reaction force, horizontal, and tension force. Equilibrium alpha 0, rotational, acceleration 0 of the center of mass. Both rotational and translational equilibrium. The previous problem is twisted. By twisting the or taking the string inclined instead of vertical, length of the rod L. You can take the torque above this point because these two forces pass through this point, cannot produce a torque above it. Then the gravity produces a clockwise torque, tension produces an anticlockwise torque. The torque produced by tension, we can calculate. So tau P is equal to tau gravity plus tau tension is equal to 0. Why it is 0? When net torque is equal to I into alpha, alpha is 0, therefore the net torque is 0. Gravity produces the torque, that is equal to mg L by 2, as we have discussed earlier, in clockwise direction or minus k-cap direction, plus the tension, the torque produced by the tension, either you can split the tension into components. This is T sin theta, this is T cos theta, this is the point. Either you take the vertical component of the perpendicular component of the force into the length of the rod, or you can take the force, this force, the force and the perpendicular distance drawn from the reference point onto the line of action of the force tension. This is equal to L sin theta. So, the tension into L sin theta or T sin theta into L, both are same thing. In the direction loss K cap is equal to 0. This will give you tension is equal to, that is mg by 2 cosec theta. That is correct answer. One. Second, find nx and ny. Write force equation. Torque equation is over by choosing this point. However, you can choose this point or this point. By force equation along x direction, net force along x direction nx along positive x direction, and t cos theta along positive x direction. Is equal to mass into acceleration of the center of mass along x direction 0. AC 0 means AC x, that is x 0. AC y, that's equal to AY, that is 0. So, T cos theta plus nx is equal to 0. So, nx is equal to minus T cos theta, but T is equal to mg by 2 by sin theta into cos theta. So, you are getting minus mg by 2 cot theta is equal to minus mg by 2 cot theta. Minus sign signifies that the assumed direction of, the real direction of nx will be opposite to our assumed direction. So, nx will be in this direction physically. This is mathematically. Answer. Next, to write the force equation along y direction. Fy is equal to m into ay. Ay is 0. So, net force along y direction must be 0. For the net force along y direction, ny minus, and there are two forces, another one force is T sin theta. Ny up, T sin theta up, mg down. T sin theta up, mg down, ny up is equal to 0. So, T sin theta plus ny is equal to mg. That is equation number 3. Now, we can solve. By solving 1 and 2, we got nx equal to this much. And substituting T equal to mg by 2 cosec theta. In the equation number 3, we are getting ny is equal to mg minus T sin theta, T is equal to mg by 2 sin theta into sin theta. So, ny will be equal to mg by 2 answer. So, in this way we can get nx, ny and tension as a function of in terms of weight and theta. So, in this case we are not getting nx is 0 when string is in this direction. In the first case you are getting nx, 0 nx, but when the string is inclined you are getting non-zero nx. So, horizontal component of the tension is pulling the rod in this direction, therefore, somebody must be there to pull this rod in this direction to make the rod in equilibrium. Therefore, nx is physically directed towards left. That is the idea, physical idea behind this problem, and we have used the concept of translational equilibrium and rotational equilibrium torque equation.